안녕하세요 여러분, 해리입니다. So in the previous videos, we have finished the basic applications and the basic methods of integration. So we've learned substitution and using the antiderivative to integrate certain functions. And also we have seen some applications like kinematics or volume of revolution around the x-axis only, and area enclosed by the curve and x-axis given the boundary. So for the videos for today and afterwards, we're going to study the integration for HO students. So if you're in SL or IGCSE, you don't have to watch it. Alright, so let's start with some further trig functions integration. Alright, so we have seen several more functions in differentiation for HO. So remember that if we differentiate secant, we have secant times tangent. If we differentiate cosecant, we have negative cosecant times the cotangent. And if we differentiate cotangent, we have negative cosecant squared. And also we have seen the three inverse functions of trigonometry. So if we differentiate arcsine, then we have 1 over root 1 minus x squared, and similar for arc cosine. And for arctangent, we have 1 over x squared plus 1 as the derivative. Then now, using the sense of antiderivative again, we can apply these later. So okay. So again, if we have secant, which is the reciprocal of cosine, then if we differentiate secant, we have secant times tangent. So that means if we integrate secant times tangent, we will have secant. Okay? And again, we're doing an indefinite integral again, so we have to add this integral constant c. So that's the first thing. Second, for cosecant, so if we differentiate cosecant, we have negative cosecant and cotangent. So that means if we integrate this derivative, we will have cosecant x plus c. And lastly, so if we differentiate cotangent, we'll have a negative cosecant squared. So integrating negative cosecant will give us cotangent. So just a bit rearranging that, we will have, so for this one, if we integrate cosecant and cotangent, that means we'll have negative cosecant. And doing the same thing for this, if we integrate just cosecant squared, then we'll have negative cotangent plus c. And again, I already explained that even if we put negative sign on the right hand side, this c constant is just an arbitrary constant, anything. So we can just, it's not exactly the same thing, but we can still just write c. Alright, so that's the first three things. So using this, we can apply these integrating methods to solve some questions, especially in substitution. So for example, one more thing. So yeah, let's not forget about tangent. So tangent is easy, but also in integration it's very important. So if we differentiate tangent, we'll have secant squared, right? So that means if we integrate secant squared, we'll have tangent x plus c. And this is very, very important later, so please bear in mind. Now, we are going to try one question, one example. So let's say we have 16 secant squared times tangent to the 4. So again, we are going to use substitution. So the reason why we are trying to use substitution is that, so remember the basic rules that, not rules, but some tips for substitution is that first, we check where the derivative exists, right? And then we substitute with the higher power. And then lastly, try to substitute the denominator. So for this one, there's no denominator. Well, we can try to make them by making this into 1 over cosine squared and sine to the 4 over cosine to the 4. But let's not do that this time. So first, let's check. So if we want to substitute secant, that means secant so if we want to so if we want to substitute secant, then we must be able to see secant times tangent inside this, right? And we see it, so maybe we could use secant. Then also, but secant has lower power than tangent, so why don't we try to see whether we can substitute tangent as well. So that means if we want to substitute tangent, secant square must exist, and we see that it exists, right? So let's substitute tangent as u. So then one by one again, so 16 is a constant, and we can move it out, and we leave secant, and we let tangent as u, so u to the 4 dx. But again, like in differentiation, in order to integrate this, we must synchronize the variables. So we have x and u and x there, right? So we don't want many variables inside the integral, so we want to synchronize the variables. So first, let's try to change dx in terms of du. So we can achieve that using this. So u equals to tangent x, that means du over dx, which means that we differentiate u in terms of x, then we will have secant squared, secant x squared. So further rearranging this, du over secant squared will equal to dx, right? So substituting that in, we have this, and this has done the job for you, so they cancel out, and simply we're doing this. So that should be very simple, right? Plus c, and u is tangent, so that should be the answer. Okay, so shouldn't be that difficult as long as you remember some of those 3 main tips. Okay, so that's it for the reciprocals and tangent. And we're going to move to the inverse. Sorry, before we directly move to inverse, a bit more on trigonometric identities first, sorry, because I think it's better to do this first. So we all know how to integrate sine, right, and cosine. So sine, we have negative cosine plus c, cosine, we have sine x plus c, and tangent, so I have already explained how we can integrate tangent using substitution, right? So change tangent into sine over cosine, and then substitute cosine, and we can find ln modulus secant x plus c, and this is in your formula booklet. So with these, let's try to integrate something like sine squared or cosine squared or tangent squared. So remember in differentiation, so when we know how to differentiate sine, cosine, and tangent, and when we are asked to differentiate something to the power, so sine squared or like sine cube or whatever, what did we do? We use we use chain rule, right? So chain rule is basically using the method of substitution, but yeah, so we use chain rule to make the function into our formula form and then carry it on, right? But integration is more restrictive than differentiation. What that means is that for integrating sine squared, sine cube, or sine to the 4, and so on, each has its own method of integrating. There is no one fixed general rule to integrate all functions. So for sine squared, you can't really use substitution to solve this, because even if you use substitution, there's nothing that, so for example, let's say like what we did for what is differentiation. Let's say we let u equals to sine x, because we know how to integrate u squared, right? Then u squared, so it seems like it's simple, but the problem is, so that dx, we have to convert that into du, right? So d over dx equals to cosine x. So doing this a bit faster, so dx equals to du over cosine x. Alright, so we can't really cancel out cosine x. That's why I told you to remember the tip 2, the first tip, where the derivative of what you're trying to substitute must exist in the given function. So you see that the derivative of cosine, which is cosine, does not exist here, right? That's why we have a problem. And well, you can try to do it by making like this, because cosine is root 1 minus sine squared. So sine is u, so that means we have root 1 minus u squared, but this is certainly not easy to integrate, and within your syllabus, within IB syllabus, you cannot integrate this. So that means we can't really solve it using substitution. Then what can we do? So our main problem is that we don't want the power. We only want non-power, so just power of 1, right? Then we can try to change this into, we can try to eliminate this power. But how? So recall some of the trigonometric identities. So for example, some double angle identities. Yeah, these. And let's see which one we can use. So for, if we look at cosine 2x, so although it's in terms of cosine and sine, but using the very basic basic identity, this, that everyone must know by now. So using this, we can write cosine 2x in terms of cosine or sine only. So if we want to write this into sine only, then we just substitute cosine squared as 1 minus sine squared. So we have 1 minus 2 sine squared. Or if you write this in terms of cosine only, then again sine squared being 1 minus cosine squared, substitute that in, you have these two. and you can see that there's sine squared, and that equals to non-power, right? So if you rearrange this, we'll have 1 minus cosine 2x over 2. So you move that there and you move that there, and you'll have that. So that means integrating sine squared is the same as integrating 1 minus cosine 2x over 2. So constant, we move it out. So simply we're integrating this, and we have two different terms subtracted, so we can integrate one by one. So if we integrate one, we have x. And what about this? So if we integrate cosine 2x, then the derivative must be cosine 2x, right? So the derivative of cosine 2x must be should be from half sine 2x, right? So if you differentiate half sine 2x, you have cosine 2x. So don't forget this half as well. So we'll have this for the answer. And let's check whether we have this result. So if we differentiate this, we have half, and if we differentiate this, we move the 2 out, half, and then we keep this angle 2x, just differentiate sine, cosine 2x. Makes perfect sense, right? So that's how we do it. And same thing for cosine squared. So you guys can try. So cosine squared, that means if you rearrange it, you'll have cosine 2x plus 1 over 2. So your result should be yeah, so this should be your result for integrating cosine. Okay, so it's not hard, it's not that difficult. Then what about tangent? So we know how to we know how to integrate tangent, right? Which yields ln modulus secant x plus c. But again, like what we did for sine squared and cosine squared, when we have to integrate tangent squared, you can't really use substitution. And you'll see, you can try. You'll not be able to do it easily. So what we can do is that, well, you can try to make this into sine squared over cosine squared and then do some computation as well. But again, that's not really easy. So we use trigonometric identity again. 1 plus tangent squared equals to secant squared, and 1 plus cotangent squared equals to cosecant squared. And please remember these two identities because they're gonna be very useful, not only in integration but also in complex numbers later. Okay, so in complex numbers later, you'll use a lot of these identities, so please remember those. Please remember this, and also all those other trigonometry related identities. Okay. Anyway, so we have to integrate that. Then let's try to change tan squared into secant squared minus 1. Why are we doing that? Because what's the antiderivative of secant squared? Tangent, right? Because if we differentiate tangent, we already know that we have secant squared. So this simply means this. That's it. So that's what it means. So again, secant squared. So you have to be very how should I say? Yeah, you should be very good at differentiation in order to get all this integration, because as you can see, we use a lot of antiderivatives. So you must be able to recall that the antiderivative of secant squared is tangent x. So when you study differentiation, don't study in one way. You have to study in both ways for integration later, okay? Especially for this further and inverse trig derivatives. So that's how we could do these trigonometric functions squared. And one more thing, so then what about sine cube? So just now I said that the method of integrating for sine x, sine squared x, sine cube x, sine to the 4 are all different. Well, if you learn something called if you learn something in complex number, so there's a way that you can convert all the power into the multiples of the angles, in some of the multiples of the angles later. But I mean, using that method, you can generalize all the powers of sine or cosine, but again, that's a bit difficult and time consuming. So, and we haven't learned complex number yet. I'm assuming that you haven't learned it yet. So for the sine cube, what we can do is that we can use the compound angle identity. How? Because if you remember sine 3x, so you can either memorize it, but those who didn't memorize it, you can just expand it out. So using the compound angle formula, we have this, right? And sine 2x, double angle identity, so 2 sine x cosine squared plus, right, so here we have cosine 2x, but what we want is that we are trying to find the sine cube, so we can change this into sine only, so we are going to use this. So that means sine x minus 2 sine cube. So cosine squared, again using this, we know that it's 1 minus sine. So 1 minus sine, that means 2 sine x minus 2 sine cube x plus sine x minus 2 sine cube x. So we have 3 sine x minus 4 sine cube x. Then rearranging this, sine cube x equals to 3 sine x minus sine 3x over 4, and you're just integrating this, and that shouldn't be that difficult. So we have this coefficient, so just move it out. So and again we have some other coefficients, but let's just keep it. I don't want to write in too many integrals. So that one will have this, right? So if we the antiderivative of sine x is negative cosine, and for that we have this, because if we differentiate this, we'll have 1/4 times this. So that's, and again plus c. So that's how we can do it, and it's not that difficult as long as you can recall the trigonometric identities. Okay, it's the same for cosine cube x. Okay, the thing is tangent. So for tangent cube x or tangent to the 4, tangent to the 5, okay, tangent is a bit easier because all the higher powers we have, what we can do is that for any tangent squared we see, convert that into this. Why? Alright, so tangent cube means we have 3 tangents multiplied to each other. So we can split this into tangent squared times tangent. So for that tangent squared, let's make it into secant squared minus 1. So that's what I'm trying to say. And for here, expand it out. So we have multiple terms, right? So that means we can just integrate one by one. All right, so the first thing, this. So again, what we can do is that we can try to use substitution. Why? Because let's say we want to substitute secant, then the derivative, which is secant times tangent, exists, right? So we can use it, certainly use it. And we can also go for tangent as well. So if we substitute tangent, will have secant squared. So either will work. But I told you to do the higher power one, but for this case, it's not really important. So you can choose anything to do. So I'll just use tangent as u. So that means du over dx equals to secant squared. So dx equals to du over secant squared. So that secant will cancel out, and then it will just yield this. And what's the integral of tangent x? It's this, right? So this u here is half u squared, right? Which is half tan squared plus minus ln secant x plus c. Right, so that's how we can find it. And it's the same for tangent to the 4, tangent to the 5, and so on, okay? So that's not simple, but yeah, so this is the integration using trigonometric identities. So mainly we are using trig identities that we've learned and we're applying these into integration. So yeah, again, you must be able to recall those identities very quickly in order to solve these integrations, okay? So that's it for the trig identity, the basic trig identity. So now let's move on to inverse. So inverse trig integration. So again, we use what we know. So using the way of antiderivative. So I mean the sense of antiderivative. So if we have arc sine, then if we differentiate arc sine, we'll have 1 over root 1 minus x squared. So that means if we integrate this, which certainly doesn't look easy to integrate by just looking at this, but we can know that this equals to arc sine using the antiderivative, okay? And similarly, we have, if we have arc cosine, then since the derivative of arc cosine is this, so we have that. And if you can notice that means arc cosine and negative arc sine are the same, right? So we don't really use this because even if we have negative sign here, we can just move it out and we can use arc sine instead. So we rarely use this, but it's also fine to use it, yeah. Lastly, arctangent. So we have 1 over 1 plus x squared. So that means if we integrate 1 over 1 plus x squared, we'll have arctangent. Okay, then using this, what can we do? So for example, let's say, so I'll not handle the easy ones. So for example, like this is not that hard because one thing, so this is 4x squared, right? But you know how to integrate 1 plus x squared, so that means why don't you just substitute 4x squared into, change 4x squared into 2x squared and just substitute that, because even so if you substitute 2x, you still have a constant, so you can, it's absolutely fine to substitute. Or if you, okay, I'll just show you in case. So as I said, 4x squared, we can make that into bracket 2x squared. So we let 2x be u, then du over dx equals to 2, so 2 times du equals to dx. Oh no, sorry. Du over 2, so half du equals to dx. Then let's change everything back. So we let 2x equals to u, so that we have u squared, and then dx is du over 2, so the constant we move it out and we have du, so it's half times arc tangent u plus c. But what's u? It's 2x, so that's it. That's how you do it. I'm pretty sure in your formula booklet it has a case where when it's 1 over a squared plus x squared, you have 1 over a arctan x over a plus c. Well, you can remember that formula, but honestly, I strongly recommend you guys to use substitution to handle these problems, because, for example, when you have something like this, let's say, then what are you going to do with this 2? So what you have to do is that you have to make this into 1 plus something squared, in the form of 1 plus something squared, where you have 2. Then some students get panicked, but nothing difficult. So we have 2, that means we make this into 1, and how do we make that? We divide the entire denominator by 2. But we can't just simply divide the entire denominator by 2, because that's affecting the equation. So instead of just dividing denominator by 2, we can also divide the numerator by 2, so that we are simply just multiplying 1, so canceling out any change. So we move the half out for numerator, and for denominator it will become this, right? And here, so we have 3 over 2x squared. Then why don't we make that into root 3 over 2x squared, right? That's absolutely fine. So that means we let root 3 over 2x be u. Then du over dx equals to root 3 over 2. So du times root 2 over 3 equals to dx, right? And put everything back. So half 1 over 1 plus u squared, and we have du, and we have this constant which we can take it out. So root 2 and 2 we can cancel and make it to root 1 over root 6, or you can rationalize it, but I'll just leave it. No. And then this is arctan u, but what's u? This. So using this way, you can also practice using integration by substitution, and also it's very, you will be more you'll make less mistake than directly applying the formula in your formula booklet. So yeah, please practice like this. And for example, if you have practiced enough and if you're confident in this, then you may use the formula in your exams to save time. But for your practice, again, I strongly recommend you to use substitution. Okay? So these two are probably the easiest examples. So let's try something more. So let's say we want to integrate something like this. So we know how to integrate this, right? So always try to use what you know. So we know how to integrate that, but we don't know how to integrate this. And we can see that there are more terms than what we know, right? So what we can do is that we can try to reduce the term. And how can we do that? So it should be very simple for you. You just need to complete the square. So for this denominator, I want to change the number, but never mind. So this is what it is. So if we complete the square, so this is what you're supposed to get. Okay, so that means that disgusting denominator becomes this. And again, we know how to integrate this, right? But we have too many things here, so we try to make that in that form. But before that, 4 is a common factor, so we can take it by root 4, which is half, and divide everything by 4. So we have this 4 and 1, right? Now we don't want this 4, so again we divide the numerator by root 4, because remember it's inside root, so we divide this by root 4. That means we divide the numerator by root 4 as well, which is half. So 1/4 over 1 over 1 minus x plus half squared over 4. Alright, so it looks a bit complicated, but you have enough paper for your exam, so just use a lot of paper, it's also fine. But anyway, so for this one, why don't we just make that into this? So half x plus 1 over 4 squared. Okay, and why do we do this? Because we can use substitution, right? So 1 minus u squared, and d over dx is half, so that means 2 times du equals to dx, right? And we're done. So that yields half, and that is arc sine u, but u is that, right? So arc sine half x plus 1/4 plus c. So shouldn't be that difficult if you. So again, the reason why we're using substitution is like what we did for equations in exponential or equations in trigonometry, equations in log. We make something unfamiliar to what we are familiar with, and what I mean by familiar is that you know what to do, right? So you clearly know what to do for this because it's in the formula. It's arc sine x using the concept of antiderivative. And what I'm trying to do is to make this given equation in the form of this. Oh wait, actually, I forgot to write an integral. Oh yeah, so right, so that's the main purpose of substitution, okay? So that's the example of like modified arc sine, and I'll do one more question. Actually, so okay, I will not go through the entire thing. I'll just tell you. So something like this: 1 over x squared plus 2x plus 7, let's say. And if you want to integrate this, again, just recall what you know. So you know how to do. So there's no root in the denominator, right? And we have x squared in the denominator, while numerator has nothing. Then what we can do is that we can try to use arctangent. But arctangent, we can apply it when the denominator is 1 plus x squared, but we have more than 2 terms, right? So what do? We complete the square, right? And just do exactly the same thing. So again, we don't want 6 here, right? We want this to be 1. That means we divide the denominator by 6, and in order not to affect the equality, we also divide 6 on the numerator, so it takes 1/6 out, and that one will become x plus 1 squared over 6 plus 1, So put that 6 inside this square. So x plus 1 over root 6 squared, and then your substitution and you're done. Okay, so I'll not I'll not do this with you. It will take too much time. So that's it for the inverse trig. And for HO, you have 2 more. So it's called the other. So we don't really have a specific name for this because you're just trying to rearrange the quotient into something that you can integrate, and you're carrying the calculation. So I'll just directly go for the example. So basically what we are doing is that we are going to look at some methods of integrating a quotient. So unlike differentiation, where if you have a quotient, a function in a quotient form, you could use something called the quotient rule, right? But integration, as I said, it's more restrictive than differentiation. So there's not really a fixed generalized rule to integrate every function. So again, when you have a disgusting quotient like this, then the only thing you can try to do within your syllabus, IB syllabus, you should try to rearrange this into non-quotient form or something that you know. So I'm pretty sure you know So if you have a quotient in the form of fx, original function in the denominator, and f prime x, the derivative of the function, then we have ln modulus fx plus c. And you can derive this using substitution. So you let the denominator as u, and then if you use substitution, you have this result. But so this is one of the one of the formula that you can try to use when you see a quotient. But for this, as you can see, you can't apply this, right? Because the denominator has lower power than the numerator. So the numerator is too big. And if the numerator is too big, what does that mean? It means, so in a fraction, if the numerator is bigger than the denominator, then what do we call that? We call that as an improper fraction, right? And what did we do when we were very young? We made that improper fraction into a mixed number, right? Then why don't we try the same thing? So the numerator has a higher power and the denominator has a lower power, then we can do long division. So so that's the quotient. Just a second, let me just quickly check whether I did it correctly. Yeah, so that's how we can do long division. And if you don't know how to do long division, please revise the very front chapters, or if I have time, I'll post that. I'll film that part as well. But anyway, so by now, if you're learning calculus, I can assume that you guys should be fine with long division. So that's the quotient and that's the remainder, right? And that's the divisor. So what we can write that down is that we make this fraction, this quotient into the quotient plus the remainder over the divisor, right? Then if we make them into common denominator, then that means we're multiplying x plus 2 on here and then adding up. That's what we have, right? So simply, if you're asked to integrate that, you're integrating this, and you can see that integrating this rearranged form is much easier than this, right? So this one we have 1/3 x cubed half x squared plus 2x. Okay, so for this one you can you can use ln directly, but if you don't know how to use ln directly, we use substitution, because all we know is this, right? So when you integrate 1/x, we have ln x. But again, using this, if the numerator is just the derivative of the denominator, then we can directly write it as ln fx, right? Okay, what's the derivative of x plus 2? 1, right? That means that we can just write it as ln modulus x plus 2. Oh, and in fact, this x must be modulus as well. So that's how we do it, okay? The reason why we're putting modulus here is, again, you cannot put negative value on inside ln, right? But for example here, just looking at this irrational function, let's say x can be -3, right? Because that just yields y equals to -1. But for integration, so when you integrate this, which means that, what does it mean by integration again? It tells you the area under the curve at the entire domain, right? So if we don't put this modulus sign, that means it's ln -1, and it doesn't make sense, right? But clearly the area must exist around that x equals to -3 or like onwards, right? So what we can do is that we just put modulus sign just in case, okay? Not just in case, but to alright, I'll just quickly explain. So x plus 2 looks like this, 1/x plus 2. This is how the graph of 1/x plus 2 looks like. So that should be the y-intercept, right? So if we want to find the area under the curve, we see it. So for example, at -3, so let's say you want to find the area between -3 to -4, right? But you see that it's negative, right? Then what we can do is that we can either flip it, right? But when you have to flip it, you multiply minus, right? But if you multiply minus on the entire function, then this will go negative. So if you learn function, if you put the modulus, so flip this part to make it into this. I mean, how am I supposed to explain this? Okay, so I'm pretty sure you know how to transform this from this to this, right? So it's reflexive over this, right? And that's what we are trying to do. So for this case, because if you put modulus there, then so okay, I'll tell you what. So clearly we know that there exists area after -2 from here, right? Just looking at this graph. So before we put all this like negative sign, so we know that there exists area here. But just looking at this function, it doesn't, right? It doesn't exist. The area doesn't exist. I mean, we cannot compute the area just using ln x plus 2 because just ln x plus 2 before -2 x equals to -2, it doesn't exist. So what we can do is that, but certainly it exists, right? So we can put this modulus sign in x here like that, then that means it's reflexive. So that's what we can have. Okay, so because what that means is that, for example, ln 1 plus 2 is ln 3, right? And that is equivalent to ln, let's say, -5 plus 2 as well, right? -5 plus 2, it's -3, but ln 3. And we have the same area for that. So that's why we just put modulus sign, okay? In order to find the area. So that's the example. Okay, I have used up too much time on this. So our other example we have is something like this. So clearly we cannot use chain substitution, right? So again, we can, and also we cannot use long division for this. So what we can do is that we can make this into two separate fractions. So this denominator is a difference of square, right? So it can be factorized like that. And what does this mean? This means that we can try to interpret this fraction as 1 over x plus something over x plus 1 added to something over x minus 1, and if you make them into common denominator, we have this denominator, right? So, but we don't know that something, so we make it into a and b. And a and b are constant, and the reason why I can guarantee these as constant is because the power of the denominator is 1. Then the numerator must have lower power. Okay, that, and lower power than power of 1, that means a constant, right? No, 0 power. So make them into common denominator, then that's ax minus a, and that's bx plus b. So a plus b x plus b minus a over x plus 1 times x minus 1 must equal to this, right? But we see that there's no term with x. That means a plus b equals to 0. And b minus a must be 1. And it's a very simple simultaneous equation. So b must be half and a must be -half. Right? Yeah, that's it. So put everything back to this. So that means this fraction quotient can be written as and again, so constant, we move it out, and we see that the derivative of the denominator is 1, right? So we can directly use ln. And same thing for this. So that's it. But if you want to write it more like if you don't want many terms, then like all those mathematicians, then what you can do is that you can make it like this. Using the ln property, okay? So the power half, I mean the coefficient half becomes the power inside the ln, right? And then subtract it, that means we divide them. So that's what we can do, okay? So that's it for the second last. So last, alright, so the last thing is integration by parts. Integration by part is the case where you use for when you have to integrate a function where the function is in product form. So it's similar to the product rule, which means that integration by part is actually derived from the product rule. So remember how we can use product rule. So if you have a product of two functions, then in order to differentiate this, okay, actually I'll not use y. So let's say fx equals to gx. Alright, so like I'll just use the same variables as your textbooks. So most of your books will use u and v. So I'll just write the function in u and function in v, okay? So if we differentiate fx, then we have u prime x times vx, right? Differentiate first one, leave the second one, and leave the first one, differentiate the second one. So this is what we have, right? Then that means u prime x times vx equals to f prime x minus ux times v prime x. And why don't we integrate both sides by x? It makes sense, right? So integrating both sides by, I differentiate both sides by x, integrating both sides by x, still the same. So this is what we have, and we have two terms, so we can separate them. And this should be just fx, right? So this is what it means, and fx is originally it's ux times vx, right? So this is the idea of by part. So when you have a product of two functions, you must define which one is differentiated and which one is not differentiated. Because depending on which one, so for example, when you have two different functions, and depending on which one is which, it determines whether you can integrate or not. So some case you may not be able to integrate. So for example, let's see a case like this. X times cosine x. Then let's say u prime. So we don't really put x here, but the reason why I use x is because all these u and v are functions of x like this. So I use x, but you can omit x. So in your textbook probably it will be written like this, but I just use this to let you understand that u and v are functions of x, okay? But anyway, so let's say u prime as x and v as cosine x for this case, okay? Then in order to integrate this, we have this, right? So then we have to find the original u, which should be this, and we have to find v prime as well, which is this. And for c here, you can omit it first because you will add at the very end, okay, after you do this. So you can just forget about it in the middle. So that one should equal to uv, which is this, right? Minus u times v prime. U times v prime, so minus half, we make it outside, and x squared sine x dx. And what do you see? You see a problem, right? Because this, can you integrate it directly? No, you can't, right? And you may be able to use by part again. So that means this is not a proper way of using by part. Then let's, instead of this, let's say u prime as cosine x and v as x. Then u must equal to sine x and v prime is 1. Then use doing the same thing. So uv, which is x sine x, minus these two. Oh no, these two. and now you can do it, right? Because x sine x should be the same. This one, it's negative cosine, but we have minus, so we have plus cosine x and plus c. So this is how we can use integration by part to integrate a function, okay? So one thing that you have to remember is that, so when you have a product of two functions, you should let one as differentiated one and one as just normal one, right? Not differentiated yet. So as you can see, for the later integral that you have to compute, you should let something, so for example, here, if we let cosine x as v, then it repeats, right? And if we let u prime as x, then it will make something if you let u prime as x, then you will have higher power, right? And you will have to find the integral of these two products, and certainly this is not desirable. So what we can try is that we let something that if you differentiate it, it just disappears. So for example, if you, what I mean by disappear is that not just disappear but becomes constant eventually. So for example, here, if we differentiate x, we have 1, right? Then what we let v as x, and u prime just be the other one, okay? Then that's the very simple case, and the difficult thing is something like this, where it's not really easy to see. So ln x, it's not in a product of two functions, right? But why are we using by part with this? In fact, actually, it's in a form of product of two functions. A constant function 1 with ln x, right? We don't know how to integrate ln x, right? Then should we let u prime as ln x? No, right? Because if we let u prime as ln x and v as 1, then we have to integrate it to find u, right? But we don't know how to do that. That's why we are doing it, right? So we are not letting u prime as ln x. Instead, we let u prime as 1 and v as ln x. Then u equals to x and v prime equals to 1 over x, right? And you're done, right? So this should be uv minus these two, and v prime, and which is 1. So you have ln x, x ln x, x ln x minus x plus c. Good. So then what about ln x squared, entire thing squared? It's the same. You let u prime as 1 and you let v as ln x squared, then dv, so v prime will be 2 times ln x over x. So you can see that differentiation must be very quick, okay? So there's no time for you to use chain rule and then do one by one in the exam. For practice, of course, you have to do it one by one, but in the exam, don't do it one by one. You will not have enough time. So practice before your exam. So anyway, so then the answer would be this minus these two. Oh, but we have ln x again, right? What do? We use by part again. So we let u prime as 1 and u is x. But be careful, can we use v again? No, because we let v as ln x squared. So this time, let's call it as v1. The reason why I could use just u prime for 1 is because they're the same. If they were different, then you should use u1 as well. So different notation, okay? Different variable. So this one, we use it like that. And then we already know the result, right, from above. So we will have negative 2x ln x plus 2x and plus c. Okay? Last example. So before we start, let's see the property of these two functions. No matter how many times you integrate or differentiate e to x will never be constant, right? And it's the same for cosine x. no matter how many times you integrate or differentiate cosine x, it will just keep repeat over and over with sine x, right? So then can we use by part for this? Because we already know that it will repeat over and over. And in fact, we can. How? So first, this time, it's not gonna be important to choose which one to be which. So I'll just let u prime be ex and v be cosine x. So u will be e to x and v prime will be negative sine x, right? So first we apply. So we apply what we know. So uv, right, e to x times cosine x, and then minus these two. But we have minus there, so it's plus. Oh, and it seems like nothing changed, right? But, well, it changed because cosine x became sine x. So maybe let's try to do one more time. So still we can let u prime as ex, e to x, because it's the same function. But this time we use v1 for sine x, because v is cosine x, so we use v1. So v1 prime is cosine x. And if we carry out the calculation, so by using by part again, u and v1, right? Non-differentiated one, so the product of two original function, and then minus these two, right? But what is this? It's exactly the same as what we had, right? Then why don't we just move this there? Right? Alright, so for this case, we have to write c because it's indefinite. And this c, where is this c from? Probably somewhere here, okay? So eventually, the integral of this will become this. And again, c, we don't put half there because c is an arbitrary constant, so it can be anything. We can let half c as another c, okay? So that's it for integration by parts. One last thing to remind you is that, so we come back to some important properties of definite integral. So why suddenly definite integrals? Because now we have learned the integration by part. So remember, in the previous video, we have seen these two properties. So we learned this, right? Finding definite integral when integration by substitution is used. And since we have learned integration by part, so let's try to find. So finding definite integral. Okay, I'll try to write it with more care. So with integration by part. So for example, let's say we have to integrate a function like this. So remember why we learn integration by part is because when we have a product of two functions and when you have to integrate that, then we try to let something be non-differentiated one and let something be differentiated one, and then use the reverse product rule to carry the calculation, right? So the main aim of using integration by part is to make one function disappear. So what I mean by disappear is that eventually become one. So you will eventually have like one function only, or as long as you make this integral into the other equation make this equation into in other form so that you can integrate. So for this case, I'll let v be x squared and u prime be e to 2x. So that means we're going to differentiate this and we're going to find the derivative of this, and we are going to find the integral of this. So u becomes this, right? Then how do we find the answer? So the main difference is that this is a definite integral, right? So calculation should be the same. So computation of this integral of this function should be the same. So remember, we leave these two multiplied, right? And then we subtract the integral of these two. So we have this, and you just need to evaluate the value at this region. Okay, so we can see that we may have to use integration by parts again. So this time, since we have already used v, we let v1 be x, so that v1 prime will be 1, and then we can still use u prime because it's the same function, right? So evaluating this, so when you put 1, so that should be half e squared minus, so when x equals to 0, it disappears, right? So we don't have to care about it. So this is what we have for this. And for this part, so negative 0 to 1, and how do we find this? So negative, so first evaluate this, right? Half x times e to 2x from 0 to 1. And then we have another integral with minus, but since we have a minus in front already, so it becomes plus from 0 to 1. And the product of these two, which is just simply this, right? So we have half e squared, and for this one, what we will have is half e, right? And again, we don't have to consider what 0 because it will be 0 when x equals to 0, right? So how do we find the integral of this? We have 1/4 e to 2x from 0 to 1, right? So eventually what we will have is this. But this time we have to consider 0 because e to 0 is not 0, it's 1. So we have negative 1/4. So that will become 3/4 e squared minus 1/2e minus 1/4. So that should be the answer for this definite integral using integration by part. Okay, so we have learned all the methods for integration for HO syllabus. So now what we have is that we have to learn some more applications of integration that are not taught in SL. So for example, area under the curve with the y-axis, and volume of revolution around the y-axis, and maybe some harder kinematics. Okay, so that's it for today. So see you guys later. Bye.